uncertainties. Today we will have two last parts of the workshop. The first one is on general assessment of reliability and uncertainty for solubility data in general, given by me and my colleague Vladimir. And the third part will be given by Joan Jacquemin about application to the gas solubility. So let's start with our part on assessment of reliability and uncertainty of solubility data. So I want to give you a list of references, so which I believe very useful as just general background of uncertainty, like GAM or VIM or Eurochem guide for setting uncertainty for measurement, some NIST recommendations, and some other publications which contain some methods used to assess reliability of data. I just again want to emphasize that the workshop is so we encourage active participation from the audience. Please don't hesitate, and please raise your hands and ask your questions. You can interrupt me at any moment. I don't want to have the formal discussion, the formal lecture. I just want to share our experience, so gathered for years of working with data, and it's not a tutorial. It's just sharing our experience. You may agree, you may disagree with our approaches, and you're always welcome to share your comments with us. So it will be great to hear your comments. Okay, before we start, I want to just briefly say what TRC is. TRC is Thermodynamics Research Center at NIST. We're located in Boulder, and our major goal, what we do, we collect, evaluate, and disseminate data on thermophysical and thermochemical properties on well-characterized systems like pure compounds, binary, ternary mixtures, and reactions. And the goal is to supply the most reliable data to those who need those data, for example, industry, researchers, academia, so they can use this data for their applications. So the basis of our work is our database on thermodynamic properties. It's called SORT database, and it contains currently about 8 million data points. And we collect this data from open literature, and we validate this data, structure this data into electronic form, validate this data, provide uncertainties to them, and then we disseminate the data either as our free product or as our products you can purchase. For example, Thermodata Engine is a very powerful engine which is linked to our database, but it contains a lot of methods, prediction methods, so ability to create your own equations of state and something like that. So, but since we have this huge source of data, so we are also working on developing models and theoretical methods based on those data, and which in turn can be used to validate those data. Which is very useful for data we are adding to our database to have additional ways to validate the data. So, but in addition to that, you probably know that we collaborate with 5 journals in the field, major journals in the field, and we provide data reports for publications publishing experimental data. Some of you are aware of this activity. You probably received some of our reports, but in addition to that, so it's already 20 years, almost 20 years we cooperate with the journals. And for years of this experience, we developed a number of tools, a number of projects to support researchers in their work. So for example, we provided a number of tools which can be used for planning the research. We have a number of IUPAC projects which support the research. For example, the project on reference systems for phase equilibrium studies, where we recommend list of systems to validate the instruments. And of course, the actual data reporting is so what we do. In addition, we now try to involve more and more modern IT technologies to facilitate the process of capturing and validating the data, because it's a very complex project. And for example, one of our activities, one of our projects is to use natural language processing to find publications which are in scope of our database and contain experimental data. And we do indexing. So if we cannot capture the data, we do indexing. We assign specific properties and mixture. We assign that specific publication has specific data, and we have this in our database. And if we need those data, we can come back to those publications and capture the data to the database. So data is just a brief overview of what we do. And if we come back to our workshop, so the purpose, everything depends on the purpose. So whether you want to assess your own experimental results, or you want to assess literature uncertainties of the data published in the literature, or you want to assess the model, assess the uncertainty for a model you have just developed, or there may be other purposes to assessing reliability and uncertainty of solubility data. And of course, everything depends on the type of solubility you are studying. Here is just a small list of possibilities. There may be others. And now let's come back to my questions I have. And I hope Vladimir will help me with the chat. So I see a number of replies. Some of them say, for example, Pablo says we use solubility data for the conceptual design of supercritical fraction processes. And Earl says for solubilities, so Vladimir, could you please help me, because I'm having a hard time to access the chat.
I can read to you, Vala, if you want.
No need to read.
Okay.
So Earl commented that the solubilities are needed to assess the effect of changes in solvent. So the accuracy and precision needs to be significantly better than the changes. Pablo also commented the values of 5 to 100 milligram precipitate active. So my case. So Miguel commented that he used to calculate for calculation purposes, to do some modeling, to develop the design of a distillation process. Another comment is to study the phase diagram and assess metastability region. It's from Ricardo Simos. From Jean, he said that the solubility I used to do also the
actually
design.
I believe anyone can read these answers, and if you don't mind, I would ask some more details from a few responses which attracted my attention. So I have a question to Earl, who says that solubility is a way to observe effects of changes in solvent. Can you please give examples of those?
Well, the solubility, as long as things are relatively insoluble, there's changes in the solubility reflect free energies of transfer from one solvent to another. So, for example, if you go back a long way, but measure silver chloride solubilities in mixed solvents, that allows you to see the change in the free energy of solution or the free energy of transfer of the solute as you change the composition of the solvent. And the purpose, of course, is to try and understand the fundamental things that are going on at the solution, at the molecular level in solutions. Why does it change in a particular way? But that's the way we've always used them.
Mm-hmm. Can we expect that at least some systematic errors can compensate if you do a series of experiments changing solvent composition?
We always tried to ensure, if you've got very small changes in the solubility, then it's going to be difficult to try and understand what's happening. I mean, we were looking at cases where the change in solubility might be, 4 powers of 10.
Wow.
Well, if you look at silver chloride in water and you add acetonitrile to it, that changes almost immediately by about 3 powers of 10. If you look at something really spectacular, but it's not solubility, but if you look at the copper-2, copper-1 reaction, by the time you've added about 10 volume percent acetonitrile, copper-1 is the stable form of copper rather than copper-2. It doesn't disproportionate. So, and of course, you're right. If you were looking at solubilities of non-electrolytes in systems where they changed relatively little, and probably fairly linearly in a lot of cases, although not always, and it's the nonlinear ones that are more interesting, but then, yes, that's why I said the experimental error needs to be much smaller than the change. If you look at it, if your experimental error is a few percent of the change, you can live with that because you can't predict better than that anyway. But if it's 50% of the change, then you don't know what you're fitting. So it's a good point.
Thank you very much.
Thank you. And Ricardo mentioned that solubility is used to determine when we enter metastable state. Can you please give examples of those cases?
Sure. When we are doing crystallization, obviously we need to know at which temperature or at which concentration we are going to get the crystal. So knowing the solubility will give us, let's say, a ballpark an idea of if I have this amount with this solvent, this temperature, I'm entering a metastable state and I eventually have the crystal. Another possibility is if I'm studying the crystallization itself, so doing spectroscopic measurements or something like that, seeing when I'm entering the metastable phase and seeing the transformations that occurred there is important. So I need to know when I'm going to start. So I'm starting before saturation. So when I'm going to start and then see the transformations afterwards. Do you want any more information?
Thank you very much, Ricardo, for this explanation. And we see from the questions, it's very live discussion in the chat, and we see that there are a number of different applications for solubility, and the level of uncertainty may be different for the required level of uncertainty may be different for different applications. Some of the applications may be very intolerable to even to small uncertainties like what Earl described. And in some cases, even big uncertainty are acceptable for some applications. So let's continue with our workshop, and let's start with the first part of assessing reliability and uncertainty for researchers' own data. Experimental data. I just want to briefly summarize on this slide that solubility experiments are very complex, and there are a number of different aspects which should be considered when a researcher does the solubility experiments. For example, reagent purities, their stability during the experiment. Some compounds may decompose during experiment, and a researcher will not notice that. So, and this will create a big uncertainty to the data. Some methods may be inappropriate to study equilibrium, specific kinds of equilibrium. For example, there was one recent publication of Professor Stiger about isothermal evaporation method, which is not an even good method to study solubility because it gives irreproducible and non-equilibrium states. What is important is what kind of analytical method you use to determine solubility. Some of them may be subject to interference to some solvent components to some additives and something like that. And it should be counted when you do this analysis to assess systematic errors. Of course, what is important, how tight is the temperature, pressure, solvent control in the experiments. So what is important is to make sure that you reach the equilibrium when a researcher does the experiment. And what is currently recommended is to reach the equilibrium from both sides, from under saturation and super saturation state, so to make sure that it converges to the same result. Also, what is important is separation of phases, because some of the mixture of the systems form stable zones or emulsions, and if researchers doesn't make sure that the system is well separated, the results may be erroneous and subject to very high uncertainties. Of course, sampling is a very great challenge to solubility experiments, and there are multiple ways. So what can interfere with this process? And I want to just give you a link to this publication, recent publication of Professor Karl Schwarz about some artifacts appearing during sampling. Of course, as we discussed during poster presentations, characterization of this solid phase is very important. So the researcher needs to make sure that he or she knows what is the equilibrium state of the solid phase in the equilibrium. Of course, there may be some effect of air, of moisture from the air. And of course, how the data are presented is also important, whether the enough information is provided for the system to characterize and reproduce the system. For example, if a researcher studies the tie lines for ternary mixture for salts without a common cation and anion, or studies pseudo components, it's important to give the final composition of the mixture because without this information, the system cannot be reproduced. There may be other aspects which should be considered. I just want to refer you to the recent publication of Professor Erich Königsberger in JCD, where some of those aspects are detailed with some examples. And please take a look at this publication. We just talked about metastability, so I just want to emphasize that you shouldn't be afraid of this metastable. It's still equilibrium, but it is metastable, and it's very common in experiments on solubilities. Here is just an example of the metastable LLE, which exists below the monotactic temperature. I just want to just give you one very interesting example from the history that metastable state is very common. For example, you know glycerol, and glycerol is frequently used as a cooling agent or heating agent in industry, and it's so viscous, it's very difficult to crystallize. And that is why it's frequently used at temperatures much below its crystallization temperature, but it doesn't crystallize. But there was an event in industry many years ago when something happened and the glycerol crystallized in pipes, and the problem was that it has a memory effect, and after that, those pipes couldn't be used to do the correct heat exchanging because glycerol always crystallized as soon as it reached the crystallization temperature. So it was a very interesting case when they simply need to rebuild the whole cooling part because metastability was just broken. Okay, another example is very common in SLE experiments, and the common example is D-glucose, when you have a number of different metastable solid phases, and even, I want to emphasize, even metastable liquid phase could exist. I just want to show you just one recent publication where authors did not provide any characterization of the solid phase. I highlighted this in red in this graph, and the problem is, without the knowledge what phase they started, so it's inconsistent with any of the curves, either stable or metastable, and it's even so the question is how reliable are those data? So without sufficient characterization of those data. So I just want to give some observations, what we see, how uncertainties are calculated in the literature. So one of common ways, but really not good way to present uncertainty is just to give bare uncertainty values without any justification. For example, they measured solubility and they give our uncertainty is 5% relative standard uncertainty without giving how this value was obtained. It's very bad way to present uncertainty because you don't know what contributions were considered so to estimate, or it's just authors believe this value. So, and of course, given this uncertainty without justification as bare value is not what I would recommend. And I would say for me, it's the same as not providing any uncertainty at all. And sometimes it may be harmless, provides some harm because it may mislead readers about the actual level of uncertainty for the measurements. So the next type of how people typically present uncertainty are just to do repeatability experiments for the final solubility and give it as typically a standard deviation of the mean. But I saw different ways how this repeatability is done. Sometimes, in most cases, what we see is they did one equilibration experiment and just simply took 3 samples to analyze, and they calculate typically very low uncertainty from this analysis, because typically analyses are have quite low uncertainty, and they give it as uncertainty of the total process for solubility experiments. I wouldn't recommend this way. Another more rare way, but the way I would recommend is when you do number of solubility experiments equilibration and take a few samples from them, and from that you calculate the repeatability. So that is the way I would recommend. Sometimes the authors, in addition to these repeatability experiments, they provide some standard uncertainties for input quantities of variables, for example, for temperature, for pressure, for mass. And they try to combine with the repeatability experiments to give the combined standard uncertainties. But the way it is done, there is a good way or not so good way. One of the ways, which is more frequent, unfortunately, is just trying to combine those uncertainties, contributions, without any justification, or sometimes just saying, we accounted this, but they didn't provide any details how it was accounted. So what equation was used to combine the uncertainties. Of course, it is not the way I would recommend. The more detailed way is to find the effect of each input variable or input quantity on the final solubility, and from this known or estimated functional dependence, estimate the combined uncertainty. That is the way I would recommend. So that is typically what we see in the literature, but the best way, of course, is to assess as many contributions as possible and provide detailed uncertainty budget, and to combine all these contributions to give this standard combined standard uncertainty. Sometimes what I would additionally recommend in this case is to do additional repeatability experiments to make sure that your assessment of uncertainty from the uncertainty budget is consistent with the actual observations from repeatability experiments. And as a result, you can get the expanded uncertainty at selected level of confidence. So just as a reminder, so for any input quantity or property, you can estimate uncertainty either by statistical methods, there are a number of them, or any non-statistical methods can be used. For example, taking the manufacturer's specifications or from previous measurements. And anyway is, I would say, equal. So they can be combined together, different types of uncertainty can be combined. And if you are interested in more details, please look at the GAM, and here is a link so below, or at the NIST recommendations on assessing uncertainties. Also, there is a link here. So I want now a few examples. I will just want to give an example of calculating uncertainties. Here is an example from the EuroChem guide on uncertainty calculations for analytical methods, experiments, and this example is just determining the concentration of hydrogen chloride with sodium hydroxide solution, which was standardized by a standard potassium hydrogen phthalate. And here is just simple equation. You measure two volumes, you measure mass of standard, you know purity of the standard, and here is the final equation to calculate the concentration from your analytical experiments. And I just grabbed the uncertainty analysis from that book, and you will be surprised how many contributions are for just these simple experiments. Here you are. So here is, I like this diagram from that book. So it's called cause and effect diagram. And it really visualizes for you the contributions to uncertainty and what is considered, what is not considered. But even if you look, there are multiple contributions to be considered. And my question to you, so please participate in the discussion. Is there anything else you can add to this analysis? Please raise your hand or unmute yourself or leave comments in the chat. Is there anything else you can add to just very simple experiment? So titration of acid with base. What else can you add to the uncertainty analysis?
I honestly doubt if it's possible to capture this complex diagram and generate an answer in a few seconds.
Okay. I understand Vladimir, your comment, but I'm just showing the complexity of these calculations, and I just want to just give you a few examples of what else can be included. Okay, Rodrigo has a comment, so please unmute yourself and add your.
I don't know if you can hear me.
Yes.
But I have the temperature calibration. You mentioned temperature on the diagram. Temperature also needs to be calibrated and very highly controlled. So for me, that would be one of the things I could add on this graph. It's temperature control. So there's an uncertainty associated to the calibration of temperature that I think should be taken into account.
Okay, thank you very much. Any other comments? You can leave the comments in chat, or I will just give my ideas about what potentially can be included. For example, if you use titration with an indicator, so the indicator will have different ranges of transition between one color to another, and the systematic error related to the indicator transition so also can be included as a contribution to the uncertainty. Or effect of CO2 on the composition of sodium hydroxide solution. So for example, if it was not stored properly, so and its composition changed even after you titrated it with a standard. Or evaporation during the test. For example, if you do high temperature experiments and the temperature leads to significant evaporation even during the test. It all contributes to the uncertainty, but it's quite difficult to account for those. Okay, this is just an analytical part. Yeah, so I see some comments about CO2 effect, oxygen effect. Uncertainty from molar mass, yes, is negligible, but still, yeah, it exists. Yeah, Earl added the bias on the endpoint. This is exactly the indicator, so effect. Okay, so this is the analytical part. So let's talk about a bigger picture. So you do this analytical part to determine the solubility of hydrogen chloride in water at specific temperature and pressure. So we analyze the analytical part. So I took it from the previous slide, but the question is, so the experiment is actually more complex. You have the calibration apparatus, you do sampling, you do dilution. And my question to you, what else should be included besides this analytical part to do the proper uncertainty analysis, to give this detailed budget? So what about the pre-analytical part? What else can be included? So please raise your hand or put some comments in the chat. I just mentioned some of the stages. You can guess from what I mentioned what can be included. Sampling error, humidity, great. It's very great. What else? Don't hesitate. You can speak up. Just unmute and talk. Temperature control of equilibration. Great. This is very good point, Earl.
I believe for hydrogen chloride, pressure is very important.
Exactly. Pressure. Anything else? Okay. So just not to waste your time. So here is just my assessment. Of course, you can add more points here. Crystal form. Crystal form of what? It's solubility of gas in water. It's probably not, crystal form is not a case for this case. Okay, pressure control, Vladimir mentioned. Temperature control, great. So also reagent purities. I think also reagent purities were mentioned by the participants. Yes. Also degree of equilibration. Do you remember in the beginning I mentioned that a researcher needs to be sure that the equilibrium is reached. If the sampling is done before the equilibrium is reached, you will have a systematic error. So, and this should be considered. Sampling, of course. Dilution. So the part when you take the sample and dilute, you may lose something during the dilution. You need to account for this. So there are multiple, you can see from this small example, very simple experiment, it's very complex uncertainty calculation. And of course, you can add many contributions to the uncertainty, but sometimes, even if you do the careful analysis and if you compare data with other publications, you frequently see that there are some disagreement between data. So, because sometimes it's very difficult to estimate all possible effects. That is why what I would recommend is to verify your equipment with well-studied systems. So that is why we initiated an IOPAC project to generate a list of reference systems with critically evaluated properties to help authors, researchers to validate the equipment and validate their uncertainty estimates. So, and we are still working on this project. We have generated list of systems for a number of types of systems for LLE, SLE, VLE. The LLE report has been already published and available online. SLE part has been recently accepted and will appear soon. And VLE part, we are still working on this. So here there are typical systems we recommend to do the validation of the equipment. So report will look like this system. It gives all data available which were considered for in our project and with an indication which data were rejected from consideration. And of course, we need some way to calculate the recommended values. That's why we provided the equations with the parameters and some tables with rounded either temperature or composition or pressure to facilitate the researcher work. Of course, many of the equations are quite difficult with multiple parameters, and it may be difficult to program those equations by researcher. That is why we also created a web page support for the authors for this project, for all kinds of, for all three types of phase equilibrium, where you could use this calculator for specific mixture you selected for, like in this case, for SLE, urea plus water, you can do the temperature calculations at specified compositions or vice versa, composition calculations at specified temperature. And we always get the results at the temperature or composition with uncertainty estimate from our model developed during this project. So please, you're welcome to use this web page. So here is the link to the web page. Okay. And I just want to summarize what I have just explained for this part, assessing uncertainties of researchers' own data. And I just want to reiterate again that solubility experiments are very complex. They're multi-step procedure, and there are multiple factors which must be accounted for, and which is important, documented. So without documentation, so it's difficult to assess uncertainty. And of course, I don't give any recipe to you how to calculate uncertainties. It's you are the artist. So the researchers are the artists. The calculation of uncertainty is an art, and whatever you do is okay. I mean, is correct. So, but the way how it's presented, it's a different story. Of course, what is better is to do the detailed uncertainty budget. But even if it's just a few contribution, it's okay. It's a valid way to estimate uncertainty. But everything, so what is done by researcher, how uncertainty is evaluated, should be well documented. Even if it's just a repeatability experiment, it's also acceptable. Repeatability experiments are also good. So just repeatability experiment. But if you give just uncertainty, just bare uncertainty statement is not a good way to present uncertainty. It's just equivalent to not reporting uncertainty at all. And of course, method validation is what we recommend. Okay, Vladimir raised his hand, please.
Okay, I would like to give a couple of comments. First of all, we are right in the middle of presentation or counting the slides, and we are over half of the time. So I propose that our presentation, our comments will be short and give the audience more opportunities to share their own methods and secrets, how they estimate uncertainties of their own measurements. And one short comment about this IUPAC project. We needed to evaluate uncertainties of recommended values. And to be honest, we did not give much attention to uncertainties of contributing measurements, because we saw that the overall scatter and inconsistency exceeded a lot claims and expected uncertainties. So probably there are a lot of unaccounted errors, and scatter was the major contribution to the uncertainty, and we considered deviation in combination with some assigned experimental uncertainty as function of conditions. And we use different methods for each system, but the point was that we try to provide two models. One model is for solubility as function of conditions, and the other is expected uncertainty as function of conditions. Thank you. And Alla, I propose that you ask if anyone wants to share their own secrets.
That is okay. What I wanted to ask. So if anyone wants to share your ways to estimate uncertainties, your observations, if you agree or disagree with what was presented here, please, you can always unmute yourself and do this. So please.
I propose that everyone can write in chat, and then we may ask someone to provide more details. So we can continue, and we'll be just watching for chat. Please feel free to give your feedback. Thank you.
Okay, so that is the first part. So the second part is assessing uncertainty and reliability for published experimental data. Of course, this method can be applied for researchers' own results as well. So there is no prohibition of using those methods. So I just want to give you just cases of typical cases. So for example, you want experimental some data, solubility data, and you was lucky and you found good, carefully done experiments with justified uncertainty estimate, and you are happy. So that is it. That is what you wanted to find, and you found. Another case, so when you immediately see that the data are erroneous, and there are multiple ways you can immediately see these. For example, you see that the sample qualities were low. You immediately see that there are some experimental problems with the procedure. For example, you know that these methods cannot be applied, or these analytical procedures shouldn't be applied. Or you immediately see some data problems like anomalies or inconsistencies. there are maybe some other indications, and researchers are experienced in their specific field may immediately see the problems. And of course, you're not happy with this situation, but you can live with this. You just disregard this data and forget about this and try to search for additional data from other sources. And so what is the most frustrating one? You see experiment which may be carefully done, but there are reporting issues. So the data are not provided in numerical form, just graphs, for example, or the data are not well defined. For example, it's not clear what substance was studied, or what phase was studied, or what are the units for the data. So there are many other reporting problems which can completely lead to the loss of data, even for good experiments, and or make the data considered to be as less reliable, although the experiments may be done perfectly, I would say. And in this case, you're completely unhappy. So you have the data, but you don't know their reliability, or you cannot use those data. And in other cases, when there are errors, but they are difficult to spot, and that's why you use this data, but they may appear erroneous in the end. So this is very frustrating cases. If we're coming back to the reporting issues, so that is why we initiated this project with IUPAC on good reporting practice, on giving our feedback to researchers how the data should be reported, so they can be used by those who are interested in the data. Of course, anyone other than readers have effect on how the data are presented in a publication. Funding agency have some rules. Reviewers give you some suggestions how the data should be presented, or publishers have some rules. But what about readers? Readers see the article in the final stage and they don't have effect. And that's why this project was initiated, to give researchers feedback on how the data should be presented so they can be used. And we have the IUPAC technical report published already in Pure and Applied Chemistry, and we generated principles on proper reporting of data so they can be used, starting from just providing data in numerical form and defining the data, also going to provide some additional information to trace the uncertainty and reliability of the data, and how the data are provided so they can be easily used by readers. So these are principles. You are welcome to go to this publication and take a look. It has number of good examples in there. I just want to give you just brief overview what we do with the data, with the publication of experimental data when we capture those data. We use our internal tool. It's called Guided Data Capture tool, and we use this tool to structure the data. We start from bibliographic information, description of all compound samples and mixtures, including purity, purification method, their source, and finally we capture data. And the capture based on the Gibbs phase rules, so where the number of state variables should agree with the Gibbs phase rule. And we capture methods, we capture units, we capture uncertainty if they are available, and finally we capture the data in the tabular form. We can always look at this data when we capture the data graphically, and you can see it's a good way to spot the typographical errors if they are present. So now we have a comment. What about uncertainty estimation as the cancellation of errors associated? Luis, could you please unmute yourself and clarify your question? Could you please?
Okay, thank you. You have just ask the people audience to make a comment about the underestimation of the uncertainty. And I just want to raise a point here is sometimes the people that are dealing with the data are overestimating the uncertainty that we can in the experimentals, as we listed in the literature, because they are consider, for instance, the temperature uncertainty twice when they are canceling in the calibration. And this is a very, very common problem. Is the people are, for instance, need capacity measurement or excess capacity measurements, if you assign the insanity to the temperature, for instance, in 10 millikelvin, and this makes a big fraction of temperature rise in an experiment, they don't care about the cancellation of this that arises from the calibration. This one is, we have experience in that here in Porto. And they have just increased our uncertainty in NIST of our heat capacity measurements for a factor of 10, when this is really stupid. And just because we listed an uncertainty of the temperature of 10 millikelvin and the temperature change in the rise of 10 Kelvin. So they consider this like a big contribution when you are, and in this case, this zero was completely canceled, the uncertainty of the temperature, because of we are calibrating the same, exactly the same conditions with the sapphire. So the uncertainty in the temperature change and the temperature of the sapphire heat capacity, for instance, was canceled there. And this was a point that I want to raise, is sometimes the people that are analyzing the data are overestimating the uncertainty.
Okay, thank you very much.
So just think about that. This could be a point to be discussed, because it's something for me is really important to not, to not change the uncertainty that is listed by us when when there is no reason for that, or they don't asking us why this is done like that. So this is something that I don't like, to see my data listed with different uncertainty than I've published. This is something that I don't like.
Okay, I will just on my next slide, I will show you sometimes why we have different uncertainty estimates. I will show you on my next slide. It may be not that only temperature uncertainty. Temperature uncertainty in the calculations typically not as big contribution to the heat capacity calculations. There may be some contributions. For example, we have some uncertainty for specific methods. We probably need to make it adjustable for different laboratories, like in your case, to not assign the typical uncertainty to your results, but the uncertainty which is much lower. So we need to discuss this and this question probably in person. So if you want to, because I understand what you mean, so that you don't want to see your data with high uncertainty than you estimated. And we can just chat if you want in person and discuss our uncertainty estimation way. So if you want to see.
Okay, thank you. It's just a point. For me, it's not so important, but it's a point that we should think about. We can discuss this one somewhere.
Okay, thank you very much. Thank you very much for this comment, and definitely we need to take this into consideration, not just based on the typical uncertainty, but also on the, I would say, laboratory-specific uncertainty. So I will come to this point, so just in a little bit, because I just showed to you what we typically do, but of course this procedure can be modified to make sure that we account for different scenarios of uncertainties. So like what we typically do, so how we do the preliminary uncertainty assessment is just we gather as much information from the article about, for example, method which is used, about calibration, about purity, about state variables, and we have some internal rules. Okay, Vladimir wants to say something.
So sorry, I would like to make a comment that I believe like all pilots have identical license, but each pilot has his or her own conditions at which he or she can land. I believe something similar should be done in metrology. Every researcher has his or her protocols and pattern, and probably approaching uncertainty evaluation based on only method is not sufficient. It's necessary to figure out the protocol and reliability of uncertainty evaluation done by researchers. And we have 15 minutes, so we need to be pretty quick. Sorry.
We actually have 20 minutes because we started later. Okay, so I just want to show that we combine this information we capture from the article with our internal rules, for example, for methods. So the way we propagate uncertainty from purity, from state variables, we look at the data scatter and assess uncertainty and get a final uncertainty estimate. And also I see the comment from Earl about that the frequently what is not what was not taken account, that some basic parts of the equipment like thermometer balances are assumed to be correct, but not really calibrated. So Earl, you can talk a little bit about this if you unmute yourself.
There's a number of examples, but I've been looking recently at solubilities, variable temperature solubilities. Oh, go away. Sorry, I'll deal with that later. Looking at solubilities of organic acids in different solvents as a function temperature. And what you find quite often is that data looks as if it's offset. So your data and my data would agree if your thermometer wasn't accurate or if mine wasn't accurate. And I come from a different generation. We had standard NPL calibrated thermometers at all the temperature ranges we used. We had standard NPL calibrated balance weight sets to calibrate balances. We had a NPL calibrated West and Cell for standardizing potentiometers and so on. Almost never, and I read a lot of papers every year in another role, but almost never do I see anyone referring to any of their apparatus having been calibrated with those are secondary standards. But the use of secondary standards in laboratories seems to me to be quite small. Or at least if people are doing it, they're not admitting to using it. And it means that right at the base of your experiments, you've got the potential for an inbuilt bias or systematic error. And you have no way at all of identifying how big it is. It will eventually turn up in the dark uncertainty if you're doing interlaboratory comparisons. But the dark uncertainty is just that. It's the uncertainty which you can't say where it came from. Years ago, I came in and calibrated a balance one day and it wasn't working. And we spent about 2 months going back and repeating experiments until we got to the point where the answers we got with the calibrated balance were the same as the ones we got when we didn't know the balance was out of calibration. But at least we went back and at least we found it and went back and did it. But we could have published 3 months of work, which was completely wrong because all the weights were wrong.
Okay, thank you very much for this very important observation about this calibration. And again, the more information researchers are providing in the description of the methods or the results, the more we can get to assess uncertainties. And this part, the calibration of the just basic thermometers or pressure meters, is a very important part to be included into this representation. I agree with you, Earl. Thank you very much for this comment. And Sima also provided a comment about the hydrated salt and the needs to measure the water content. Sima, if you want to unmute yourself, please, you can do this and comment.
Well, Hala, it's just a thing that I find many times when people are publishing results at different salt molalities, people many times don't really explain how they measure when we have hydrated salts, because many times the water content of these salts change with time in the place where you stored them, and you have to take that into account in order to make in a intelligent way and find the uncertainty associated with. Because, for instance, we use different operators doing that by Carl Fisher. We measure at different times. We use different masses of the salts. We even sometimes dissolve the salt in a given solvent that previously we have measured water content in order to find what it is, and then to have like a uncertainty dependent on the molality you are calculating. And in fact, many times you cannot find in published papers and in very good journals, you cannot find that. And I think this also a thing that it is the start of your work. So I just want to make this contribution because I find it important to take that into account also.
Okay, I want to give one more example about hydrates. It's very often that solubility of hydrates are measured in aqueous solution of organic solvent. And it's frequently what we see, authors don't report the final state of the hydrate in the solution, especially when they go to the, for example, alcohol-rich side of this solvent content, and they don't determine whether they still have the same hydrate or it decomposes. So that is one more problem with hydrates. And unfortunately, this is a very complex question, and hydrates are very difficult to study in general. And coming back to Luis' comment about the contribution for the heat capacity measurements. So we have this observation that although we have the same method applied, it may be applied differently in different laboratories, different protocols, and the uncertainty variation may differ by, like in the case of heat capacity measurements for ionic liquids, by even 10 or 100 times. So you can see, so whatever, you see the same method, but completely different levels of uncertainty. And uncertainties are laboratory specific way. So not method specific, but laboratory specific. And I agree with you, Luis, that we need to sit and discuss the way to avoid these, to account for this laboratory effect, I would say. The protocols used or something like that. I agree with you. So, but this is just, what I just explained was just the first initial assessment of uncertainty. What we do, we further, it may take very long time to assess the final uncertainty. So we do multiple levels of checks, and the methods, so the checks are typically done so by applying different comparisons. And the methods are described in more details in this publication by Vladimir. So you can take a look at C examples. And what we typically use, we use the capability of thermodata engine to do this assessment. For example, so when we just load the data into the database and we see some deviations, or we need to do some more rigorous uncertainty analysis, we need to go sometimes deeper into the content analysis of the article to see the methodology in more detail, to see the effect of the sample quality. Sometimes we compare with other available literature data, with endpoints from other authors or literature. We compare with predictions and correlations. We can compare with models, with different properties, even within series of compounds, for example, families of compounds. And there is multi-level checks done at NIST, and you can, if you're interested in this, you can use any of those. You can contact us. We can help you with those. I just want to show you a few examples of the checks. So we do. So I just let's talk about content analysis. For example, you want to look at the solubility of a compound which has which is optically active. And unfortunately, a paper you found doesn't specify the composition of whether it's R or S, one enantiomer or another, or it's a mixture of them with composition either known or unknown. You don't know. The article doesn't say anything. And here is a typical phase diagram for such enantiomeric mixtures. And it may be just form simple eutectic, like in this case of ketamine, or menthol can form intercomponent compound, and the phase diagram looks like this. And my question to the audience, will the solubility in any solvent depend on the stereoisomer ratio of the studied sample? You can unmute yourself and give your comments. So you have a sample, you don't know its composition. The question is whether its solubility will depend on the stereoisomeric ratio. Earl, I think you have experience with this. You can comment.
Well, from finding from looking at the organic acids, where you have a number of isomers possible, the answer is yes. It's quite. I was quite surprised when I first came to it, how big the differences in solubilities can be. So it absolutely does happen. And as you quite rightly say, there are people who don't tell you what they've measured, and it's not really very easy to figure out what to do with it. But I was surprised when I first came to this, how big in some cases difference in solubilities are. But yeah, they're significant.
Yeah, Earl, you're completely right. The difference is huge. So especially when there is a very big dip, like in the case of ketamine, 30-degree difference in the melting point of the pure enantiomers or racemic mixture. It's the difference in solubility will be significant, very large, and it's valid for any solvent, either it's optically active or not optically active. It's valid for anything. So let's take a look about other check is comparison with literature data. So we can do it in thermodata engine, like in this case, an article on solubility on LLE for paraxylene plus water. So we found a paper, we compare it with numerous available literature data, but we immediately see that there is a problem, at least on this site, with the data. They differ from other literature data. And Vladimir has recently published a paper which allows you to simultaneously see both sides of the curve. So it's called composition stretched coordinates. So where you can see both sides simultaneously and see magnitude and difference on both sides simultaneously. And in this case, yes, there are problems on those sides. They are inconsistent with numerous other literature data. And it's no surprise if you look at the method, if you look at the content analysis, content of the paper, cloud point method is not the way to study low solubilities at all, because one drop is more than sufficient to reach the solubility limit for such cases. And this is not the way to study low solubility. So this is a combination of approaches of comparison with literature plus content analysis. Another case I want to share with you, I still have a few minutes. It's about D-glucose plus water. Do you remember this complex diagram I showed to you? So, and we found a paper, so just recent publication where they claim, so they found the report the solubility of glucose at high temperatures, and they claim good solubility with a handbook of 2003 Yolkovsky handbook. And they emphasized on every page of the article that they have good consistency with that book. So, and but the problem is, you see the units is gram per liter, but they don't specify what liter is that. So whether it's per liter of final solution or it's per liter of the solvent. But if you look at the values of the solubility, you can see 3 kilogram per liter. It's definitely, it cannot be per liter of final solution, because it's much larger than the density of glucose. So it's clearly the liter of the solvent. So in this case, if you look at the content analysis, you see this kind of very complex analysis method, method for measuring solubility, starting from saturation, dilution, cooling, sampling, and chromatography analysis. But if you look at the formula, they give the mole fraction calculations, but the equation is definitely wrong, because they assume the same density for the solution as 1 gram per liter, which is ridiculously impossible for this method. The formula is incorrect. So, but they also give the graph of the mole fraction solubility versus temperature. I digitized the plot just to make sure that whether they did the conversion correctly or not. And it appeared that the data taken from this table and from this graph digitized, you see nearly no difference. That means they didn't use this formula. It's okay. At least they did some calculations correctly. So more detailed analysis, I found their previous publication from the same system. But what I didn't like, that they were inconsistent. Even the difference is 1 year difference in the publications by the same author. But the rest, there are inconsistencies in the data never discussed in the newer publication. So, but then I decided, okay, let's apply this comparison with literature. And I want to just emphasize that if you take just random literature for comparison, you may be mistaken. Like in this case, I just took the one more recent publication from other authors and these yellow dots and tried to compare it with this current, with the case study article. And they were generally not so consistent, but not so bad, I would say. Not bad. But the problem is that this yellow publication, they measured data at different pressures. But the article we are considering right now, they never specified what pressure they studied the solubility at, never specified. So that's why it's kind of one more stone into the pool of this article. But then what we decided just to gather as much information as possible. It's already done actually in our database. And oh, but by the way, I forgot to mention that this yellow article, they compare their data with the case study article. That means that they were result aware. So that it's not a good article to compare, because those authors we compare with, they knew about that publication and they say, oh, there is a good agreement with that publication. Okay, let's compare with other data. You can see that if you gather other sources, at least 14 sources, you see huge difference in with multiple sources. And of course, we mark this data in our database as erroneous because it's completely nonsense data. And just if you look at the history of this, so there was an error in the handbook, because you remember I mentioned in the beginning that they compared with this handbook and they claimed good consistency. I looked back into this handbook and they simply made a conversion error. So when they calculate, because they compared with, they used the data from these black sources, but they made some conversion error in the handbook, and this error, so propagated to the error in the article when they tried to compare. I even don't know how they did the experiments to match with the erroneous data in the handbook. And then later article again studied the erroneous data, and it's completely blown up the case. And Vladimir wants to talk about this.
Ale, it's already 9:15.
We have about 3 minutes. Okay.
Yes, for sure. Yes, Hala, we have at least more 5 minutes, please.
Okay.
And please give me 1 minute at the end.
Sure, Vladimir.
Okay, I just want to give a brief, very short comparison with prediction. So one of the methods. So here's VLE studies for compounds different by one CH3 group. And the dots are experimental data, and line is just UNIFAC prediction. You can see huge difference in relative volatility by 2 times. And the question is, who should we trust, the experiment or the model, the prediction by UNIFAC? And if we to validate what should we trust, we just took a well-studied system, propanol plus ethanol, and we took experimental data and the prediction by the same method, and they were consistent with each other. And it's no surprise, because there is very small difference in the boiling temperature. That's why you don't expect much difference in the composition of the liquid and gas phase. And you can see the volatility were consistent in that case. And the question to the audience, so what do you think about the cost of error in VLE? Do you remember I mentioned in the beginning that some applications are very sensitive to errors, some of them are not. And since we have little time, I will just show a very nice diagram by our friend Supat Vatanasiri. He made the calculations for industrial applications of VLE for the case with low relative volatility between compounds to be separated, and even 5% in error. So leads to the doubling in size of the distillation column. But in our case, in the case I showed to you, there were 2 times difference. I doubt that any engineer would increase the column in such a way that to account for this error. They would probably redo the experiments in their own laboratory to make sure that the column will work properly and to make sure the size is appropriate. Okay, and we apply also checking consistency with other properties using AC models like Wilson model. We did it for sulfalan plus water for our project on reference systems. We had the SLE data verified with the use of other data, VLE and excess enthalpy, to make sure that all properties are consistent with each other, to make sure that the experimental data presented on SLE were correct. So they, at least they are compared with other properties. Another way for checking consistency is building family trends, like in this case, LLE of toluene plus water and ethylbenzene. And we tried to show that the family of LLE, they have a regular changes in the solubility, which also proves our choice of the systems as reference systems for verifying the instruments. And some takeaways. So GRP is please follow GRP when you report the data to make sure that the data are not lost. The more information is provided in the paper, the better. So the better the readers can have ability to assess the reliability and uncertainty of data. And you can apply different checks on different levels. Again, as Luis mentioned, that each laboratory has its unique uncertainty pattern, and just method is not sufficient. And just good consistency with literature may be misleading. You just saw from the example. And Vladimir, you can comment. Please.
Okay. Once at the conference, I asked a colleague how he estimates reliability of published data. He told he measures one point, and if he confirms it, he likes trust the rest. Unfortunately, that colleague disappeared when I tried to contact him. And all these verification, validation methods which we considered today, I would say they are invalidation. We reveal to what extent the data can be challenged, criticized, inconsistent, but it's much more difficult to set the upper limit of possible error, to say that we know for sure that these data are reliable until this limit. So my feeling is that we need to give both estimation as our knowledge increases. This gap becomes narrower, and unfortunately we have little time to ask about your experience, so probably you can quickly say something. And as we need to publish results of our discussion, please feel free to contact with your input. Thank you.
If anyone have any comments, you can write in the chat. Or so because the chat will be open, I believe Timao, it will be open. You can leave your comments during the break. You can leave your comments by writing to us directly. So you're welcome to contact us.
Yes, Hala, the session will be open. If somebody wants to introduce and still share about this talk, thank you very much for this very interesting talk and for sharing your experience on this matter. It was quite a pleasure to listen from you, and it was really very dynamic, very interactive. That was really very good. We don't, unfortunately, have much time now because we have just 15 minutes break before to start the next activity of the workshop. I'm pretty sure that many of us have a lot of things to talk to you, and we will do it by email or by other means. And thank you very much for your participation and collaboration. Thank you a lot. We will start the next activity by 15 minutes, so let's say at 16:40. Thank you very much. See you in a moment.
Thank you, Simao.